So, you're gonna have a test. It's gonna be nice and short, super simple. You need to know.
Like the midterm?
I know.
Sure. What do you need to know about pendulum motion?
That's T and the LG one.
Yeah. So we know that the period is equal to 2 pi square root of L over G. So really the only thing that changes there is length of the pendulum affects the period of the pendulum. Which means if I'm already recording this. So if the length is bigger, then the period gets
Bigger.
and if the length gets smaller, the period gets
Smaller.
hey.
That makes sense.
So if G changes, how would G change?
If you're on a different planet.
If you're on a different planet, then G would change. So if you're on a smaller planet, G would get smaller. And if this gets smaller, then this would get bigger. Or if you went up in the mountains, then G would get a tiny bit
Smaller.
So T would get a tiny bit
Bigger.
Okay, so that's stuff. Okay, and then we had the bouncing spring equation that looked really similar to this. It still had 2 and pi, except this time it had
Michael Kors.
M over K, and K was how springy the spring is. Springiness. And M, of course, is the mass. So, if you have more mass, you want to have a slower period. So bigger mass, bigger period. So, yeah, that's why if you look at your guitar strings, the ones that vibrate at a low frequency are
Thicker.
The bigger mass has a natural frequency that's lower
Hey, wasn't
Hey,
that
it
a
almost
question
like
on
works.
one of the tests?
or something.
I remember that. Yeah, never mind.
So if you understand that, then you will get those questions right.
I don't even
Then
understand that.
we're going to have a couple projectile motion things. In projectile motion, you need to understand that if we are going up, we're going in both 2 directions. This component is going at a constant speed, and this one is accelerating. So it's going to get slower, 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 stop, and then get faster, faster, faster. Like normal stuff, right? So of course, if you have this angle and you have this velocity, then this side we find using sine, and this side we use using cosine, and that's really easy. But the vertical component is governed by acceleration, and the horizontal component is governed by constant speed, and so that's gonna just keep trucking like that. So yeah, you guys have all dealt with those, and you actually were successful in that unit. Then we had
I saw a little way.
Then we had a question about friction and stuff at an angle. So if we have a box on a ramp, what's trying to pull it this way?
Gravity.
The parallel portion of its weight, which we find by taking sine of the angle times the weight. And what's trying to keep it from not moving?
Friction.
Friction force, which of course is
UMG.
UMG cosine theta, because, yeah, and the angle, of course, is the angle of incline. And so if F parallel is bigger than FF, it will slide and accelerate downward. If they are equal to each other,
It won't move.
it won't move, but if you give it a bump, it will move at a
Constant speed.
constant speed. And of course, if F parallel,
Yeah.
what a dork.
There's 2 and
There. So there it will slide. And of course, if FF is greater than F parallel, then it just sits there. It doesn't go zooming up the hill.
That would be very smart.
That would be very interesting if we started accelerating us all over the place. Definitely not.
Michael Jackson would be like,
So yeah,
does that mean anything?
and then we're gonna have a momentum equation,
Oh, momentum. What's it?
Momentum.
and you have
Just one momentum equation?
It's not even that good. It's
well,
all the same.
it's
We'll
a
have to both
compound
create
problem that you've seen before,
elastic
and all they have is P equals mv on here, right?
That's right. I was just
And delta P equals F delta T. So
We need to go.
okay, fine.
Just play it.
So of course momentum.
Love you. No matter what happened.
Make that take a
I'm leaving, guys. We will accept you magnet either
Make
way.
some money.
You guys look cute. Make some money. Go to your funeral.
So and we know that the P equals MV before has to equal the P equals MV afterwards, right? So there's a lot of different ways to do that, but say you're running down the street.
Sorry. I'm looking for a Joanna Matei.
Aren't we all?
Ms. Rodriguez is asking if she can go to her classroom.
As soon as she can. Okay.
Thank you.
I realize that she's being recorded for posterity. So say you have 100 kilogram mass and you're running at 5 meters per second, and you go and you jump onto a really heavy skateboard. So say you have a nice weighted down skateboard, you put a box on it,
Why?
and so you're going to jump on top of that skateboard. If the skateboard has a mass of 10 kilograms, that's why we had to put a box on it so it has some sort of appreciable mass.
Oh, okay.
If the skateboard is just sitting there and you're running along and then you leap on top of this, assuming you have some sense of balance, it'll come zooming along. But again, the total momentum before has to equal total momentum afterwards. So afterwards, you're going to be standing on top of here, having fun. Whoops, wheels go here, stupid. So now you're going along. So initially, how much momentum did the skateboard have? Yeah, so that was 0 meters per second. And so now we want to know, well, how fast are we going over there? Well, the total momentum before was 100 times 5, or 500. So the total momentum afterwards still has to be
500.
500. But this time it has to equal, again, MV. And the M this time is my 100 kilograms and the 10 kilograms.
110.
So that means this is 110, which means the V must have slowed down too.
Sorry.
Something less than 5?
Yeah, I'm thinking something less than 5.
Well,
Like
then
this
we got a
was
good
less.
start.
Nobody has a calculator.
I'm 500 divided by
I don't.
4.545554. I just said it. Fine. Don't take
Think I
it.
care?
Wow.
So now you're going at 4.545454545454544 ad nauseam ad infinitum. Right. Okay, so that's super simple.
So you just have to like think along those lines. Then we are going to have some series and parallel circuit stuff. Because everybody loved that. So
this is how we would draw it if this was a 10 and this was a 20 ohm. And this is 12 volts. Say we have 10 and 20 ohms that are hooked up like this. Well, if I hook them up in parallel, if I just tell you in words that they are hooked up in parallel, you would draw it this way. If I say that they're hooked up in series, how would you draw it?
Together.
In a little rectangle, so you can have it. So then
Just
we
like
have
you
our
added some
10
extra
and our
value on the
20,
first
and
one.
we look like that. So,
Extra cell, whatever you call
so if I want to know what is the effective resistance, how do I add up effective resistance when they're in parallel?
it. 1 over inverse.
Yeah, so 1 over 10 plus 1 over 20 equals 1 over RE. And so that would mean my RE is 10 to the minus 1 plus 20 to the minus 1 equals to the minus 1. And I get 6.666666 ohms. Now, if they are in series, how do I add up to find the effective resistance?
Just add them all up.
I just add them.
Wow. Look at that.
That was way hard, right?
Way
So,
worse.
if I want to find the current, I of course is equal to D over R. But here, since there's two different pathways, then there's two different currents. So I'm just going to have 12 over 10, and I'm going to have 12 over 20. So that would be 12 over 10 would obviously be 1.2 amps going through that wire. And 12 over 20 would be half of that, so 0.6 amps going through that wire, which means how much would be going through this wire? If I have 1.2 going through here and I have 0.6 going through here, then how much is going to go through here? It's going to have to pull enough current to go through there and through there. It branches into both. So I just add those two up and I get
1.8 ohms.
So how much power am I using over here? Well, power of course equals IV, and the total current I'm pulling here is 1.8 amps, and the total voltage I'm pushing with is 12 volts. So 1.8 times 12. It's going to be 21.6 watts. Now, we're over here on the series side. Am I going to use more power or less power? Oh, yeah, if you look at the resistance here, the resistance is higher than it was over here. So if the resistance is higher, then the current's going to be smaller, so I'm going to use less power. These are less bright, these would be more bright. Remember when we played with light bulbs and everything? Yep. Right. Okay, anyway, so I, of course, here is still going to be V over R, so we're going to have our 12 over the total of 30 because there's only one pathway, so we have only one current possible. So 12 over 30 gives me 0.4. So up here I have the current of 0.4 amps. And how much voltage is each one of these going to use? Well, over here, again, all 12 volts, we're going to lose 12 volts here, and I'm going to lose 12 volts here because I have to lose all of it to get back to the battery. But here it's going to be proportional. I'm going to use 1/3 of it here and 2/3 of it here because if you add them up, it's 3. So, yeah, so we can just say V equals IR again to find out how much voltage drop we lose. So 0.4 times 10 is going to be
4.
Thanks. So I'm going to use 4. I'm going to lose 4 volts going across here, and if I have 0.4 times 20, I'm going to lose 8 volts going across there, and of course 4 volts and 8 volts adds up to 12 volts. What do you know? It's gonna lose all of it. Again, you can just look at proportionally. This is 1/3 of the total. This is 2/3 of the total. Hey, that's 1/3 of the voltage. That's 2/3 of the voltage. It should all make sense. It's kind of logical and stuff. So here you'll have full voltage drops. You have different current levels. Here you have the same current level but different voltage drop. It works out like that. And again, the power is going to be IV. So this time the total current is only 0.4 amps. Last time we had 1.8, so we were pulling a lot more current with that same voltage of 12 volts. So 0.4 times 12 gives you only 4.8 watts. So you're going to spend less money on the right one. The left one's going to be a lot brighter. See, 21 versus 4. That's a substantial difference. So yay! That was electricity, and we did pretty well on that one, and that was recently and stuff. And of course, once we found the power, this power turns into heat, and Q of course equals MC delta T. Did that one show up on the formula chart? Doesn't look like it. Good, I'm teaching you extra stuff. I like that. Yes, there's much more physics to teach here, but okay, so if I want to know how much hotter it got or whatever, you can solve that. And M, of course, just stands for mass, delta T is the change in temperature, and C stands for the specific heat. The specific heat of water, of course, was 4180 joules per kilogram, degrees centigrade.
Water.
That's water, specific heat, if we're heating up something in water.
C is the specific heat, right?
Yeah.
I heard 1. Is the time in any terms, like is it in minutes, seconds, or?
The time where?
For the, yeah.
That's temperature.
Oh, okay.
That's changing temperature, not changing time. But time is always in seconds whenever it's in a formula. So
Now I know.
yeah. Well, we have power. Power is work over time. I'm sorry. We do have time here. The P doesn't equal the Q. The W equals the Q. So the work done is the Q. So the P has to come up next to the T. So after we have power times time equals MC delta T. Sorry.
Okay, I just
So,
really know.
the work done turns into heat, which is Q. So we worked out problems like that before. And everybody loves it. The last thing that's on your test, it's that short, man. Whoa, this is so short.
We do just.
I'm not gonna make the joke. The last thing we're gonna do is torque, and torque, of course, we had fun doing torque problems, and yeah, so we had mobile problems. So just put 2 of them over. It's more fun. So let's say this thing is 1.5 coulombs and it has a length of 1 meter. And this one has 1.0 coulombs and it's only 0.7 meters long. And we have this mass is 1.3 coulombs. And this one is 2.5 kilograms, and that one is 0.75 kilograms. And yeah. So now we have a bunch of masses, we can need a bunch of distances. We know this whole distance is 1 meter. Let's say that this this string is hanging right at the 40 mark, which means this whole length is 40. And so from the midpoint, this one is hanging at, say, the 85 centimeter mark, which means this distance would be 45, and this one's hanging at 90, which means this would be 50. Hey, so this one's gonna go with 50, and this one's gonna go with 45 for torque. And the weight of this stick, if the whole thing is 1 meter, then the midpoint would be at 50, which means that distance would be really 10 as far as torques go. So on this, we're going to have, this weight is going to be trying to torque clockwise and clockwise, and this one's going to be clockwise. Right? So my total clockwise torque has to be, you just add it up. So 1.5 times 10 plus 2.5 times 45 plus 0.75 times 50 equals that gives us 165 as a total torque clockwise, which means my total torque going this way must also be 165. So we know this has to be 165 as the total torque, which again is going to be force times the distance, and the force and distance are perpendicular here. So let's say this is right at 10. That means the total distance from here to here must be 30. So if the D here is 30, then the F must be 5.5. So the total pulling down on this string must be 5.5 kilograms. So then we say to myself, well, hey, if this is 5.5 kilograms, I know the mass of this is 1 and this is 1.3, which means this round thing must be the rest of it. Minus 1 minus 1.3 equals 5 minus 3 is 2. 5 minus 1 and minus 1 is 3. So we already know the mass of this round thing must be 3.2 kgs. So now we just got to say, well, how does these three things torque over here? So just to be obnoxious, we'll switch to a different color here. So if this thing is 0.7 ohms, that's the total. So that means 0.35 would be the midpoint here, right?
Yeah.
And so I'm gonna say this is right at 0.4 just to make it fun. So how far over is that one?
0.05.
Yeah. So we're gonna have 1 times 0.05 for a torque going this way, and then if we have this one set at, say, I don't know, 0.2. So if this is at 0.2 and the torque is, or the pivot point is at 0.4, then that's a change of 0.2. So we're going to have 1.3 times 0.2, and this one will also be counterclockwise, and so this puppy must be clockwise, right? So then we're going to say we have our 1 times 0.05 plus the 0.2 times the 1.3. These are both going this way. They have to balance out the what we know is 3.2 going, I don't know, how far over is that So that's what we gotta figure out on that. So clearly do this part. 1 times 0.05 plus 2 times 1.3 equals. and
Wait,
that
you
gives
mean
us
0.2, not 2, right?
2.65 equals 3.2x. So clearly I need to divide now by 3.2, and that gives me x is 0.82. I need a longer stick. So from here, I'm going to go over 0.828. I'm thinking I'll have it worked out better on the test, so we don't have a stick that makes me put this out in imaginary land. That just doesn't seem right, though. Okay then.
That worked.
There isn't gonna be anything about leaves.
That doesn't seem right.
You made it up on the spot.
No, I understand it, but I'm just still, it's like, these two are very small and this is very big, so I would have thought that this was gonna have to be really, really close.
It's okay. The math adds up. 0.05 because
No, the
it's
math does not add up because that's this 0.8 and the entire stick is 0.7.
This is practically on the thing, so this one is very, very small.
that happened.
And then this one isn't that big. This one isn't that big compared to the mass is huge, so that should be a smaller distance. Did I plug in did I miss a decimal here? Is no one checking my math?
I was, and then you said mean things.
I was hoping more
Stop
so
doing
far.
that.
Yeah, see? I told you, you gotta go with your gut instinct here, man. Okay, so this total was 0.31, thanks for checking my math, people. Equals 3.2x, that's what I thought this is gonna work out fine. Okay, so now we divide by the 3.2. And we get 0.096, which is much more reasonable, so now this thing's gonna be just over this way. 0.096875. Hooray! Stupid, bah. That
That's
never
the whole
happened.
problem.
That never happened. We forget about it right now.
Okay. Not that you guys ever make mistakes like that, but at least see, I looked at that and I said mentally that doesn't make sense.
I always do that.
And you gotta do that. You can't just say, oh yeah, that's the answer without thinking, is this reasonable looking?
But then I just draw a
Because if
sad
this is
pig
quite a
like
bit
that.
heavier than that, then it should be closer,
I
you know
draw
what I mean?
like a sad face like that. Super
So that's it?
Woo.
No,